In this video, I'm going to show you how to calculate the Jacobian matrix in cylindrical coordinates. The Jacobian matrix, here denoted as JF for Jacobian of the function f, is defined in such a way that it contains all possible partial derivatives of a vector-valued function. What that means is the following. If our function f is a vector, that vector is obviously going to have multiple components. The higher the dimension, the more components. For the first row of the Jacobian matrix, we're going to take the first component of the vector and differentiate it with respect to every variable. So if the components of our function are f1 up to fn, and the variables of our function are x1 up to xn, then we're going to start with the derivative of the first component with respect to the first variable. We're then going to move on with the derivative of the first component with respect to the second variable, etc., until we run out of variables. In the second row, we're going to do the same for the second component, etc., blah, 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 until we run out of components. Which means that the number of components of our vector determines the height of the matrix, and the number of variables those components contain determine the width of the matrix. In our specific example, we're looking at the transformation from Cartesian coordinates to cylindrical coordinates. And that transformation looks like this. Every x turns into r cosine phi, every y turns into r sine phi, and the Cartesian z is kept the way it is. That means this will be f1, this will be f2, this will be f3. So we have 3 rows, and we also have 3 variables, r, phi, and z. So our Jacobian is going to be a 3 by 3 matrix. And that matrix is going to look like this. So now let's compute all of those derivatives so we can fill this matrix with the actual values from our transformation. Del f1 over del r means we have to differentiate the first component of our vector with respect to r. So if we differentiate r cosine phi with respect to r, the r turns into 1 and only cosine phi remains. Next, we again have to differentiate the first component, but this time with respect to phi. That means we're going to keep this r as a constant, and the derivative of a cosine function is minus sine. So we get minus r sine phi. As a last step for the first row, we have to differentiate the first component with respect to z, and as we can see, there is no z, so this is just going to be 0. For the next 3 derivatives, we're going to have to look at the second component. Differentiating r sine phi with respect to r gives us sine phi. Differentiating it with respect to phi gives us r cosine phi, because the r remains as a constant, and the derivative of sine phi is cosine phi. And for the last entry of the second row, we would have to differentiate with respect to z again, but there is no z, so this is going to be 0 as well. For the third row of our Jacobian matrix, we're going to have to look at the third component of our transformation, which is simply this z. Z differentiated with respect to r is simply 0. Same for the derivative with respect to phi. And z differentiated with respect to z simply gives 1. So this is the final result for our Jacobian matrix for the transformation from Cartesian to cylindrical coordinates. Now you may be asking yourself, what the heck do we even need this for? And the main use for this is transforming volume integrals. So suppose we have a triple integral in Cartesian coordinates. That integral is going to use the differentials dx, dy, dz. Each of those is a tiny, tiny length, so length times length times length gives a tiny, tiny volume. Now the problem is, if we transform this into cylindrical coordinates, our differentials are also going to reflect the variables of that coordinate system, so we're going to have dr, d phi, dz. However, length times angle times length does not give a volume. For the integral to work, however, this needs to be a volume. So we need an additional factor that we can multiply with those differentials in order for the volume element to actually become a volume. And the way we can find that additional factor is with the determinant of the Jacobian matrix. And that's what we're going to do in the next video. If you found this video helpful, consider leaving a like or sharing it with a fellow student who might also benefit from it. Thank you so much for watching, and see you in the next one.